Hey everyone, and welcome to Inside the Lab. Today we are talking about what it's going to take to build next-generation displays for virtual and augmented reality. Now, making 3D displays that are as vivid and realistic as the physical world, it's going to take solving some fundamental challenges that we're going to get into today. And these are some pretty interesting problems because they're all about how we physically perceive things and how our eyes process visual signals and how our brains interpret them to construct a model of the world. It all gets pretty deep, and I have some new prototypes to show you today that we've been building in our labs. And then Chief Scientist of Reality Labs, Michael Abrash, is also going to join us today too. But first I want to talk for a few minutes about why this matters. Displays that match the full capacity of human vision are going to unlock some really important things. The first is a realistic sense of presence. And that's the feeling of being with someone or in some place as if you're physically there. And given our focus on helping people connect, you can see why this is such a big deal. The other day, I was testing some of our work on photorealistic avatars, and it was a mixed reality experience, so you can see around you, your surroundings, the room you're in, everything looks like it would if you took the headset off, except there's a person right there with you. And you can walk around them, you can see them move, you can get the sense that they're really there. And you can imagine that if that was someone in your family who lives far away, or someone who you're collaborating on a project with, or even an artist who you like, you can imagine what it would be like to really feel like they're there with you and that you're physically together. So that's presence, and that's what I'm talking about when I say that word. Now, another reason why these kind of realistic displays are so important is that they're going to unlock a whole new generation of visual experiences. And this is part of the story of technology and culture over time. And we've seen that our culture evolves to adopt the levels of depth and richness that our technology can provide. And then the next thing comes along and it opens up new forms of art and individual expression. People have a deep desire to feel understood. And so being able to express yourself in as immersive and realistic of a way as possible is very powerful and important to us. And we've seen this since the beginning of our company, as the mediums that we use to express ourselves just keep growing in richness and depth. And we're in the middle of a big step forward towards realism and creativity right now. It's not going to be that long until we can create scenes in basically perfect fidelity. And only, instead of just looking at them on a screen, you're going to feel like you're there, experiencing things that you'd otherwise never get to experience. And that feeling, the richness of that experience, that's why this sense of realism matters. So current VR systems can already give you a sense that you're in another place. And it's hard to describe how profound this is. It's something that you kind of need to experience for yourself. But we still have a long way to go in the displays and graphic stacks before we can get to visual realism. And the reason here is that the human visual system is deeply integrated. So just seeing a realistic looking image alone isn't enough. To get this feeling of immersion, you need all of the other visual cues as well. And this is a much more complex problem than just displaying a realistic looking image on a computer screen or a TV. You need stereoscopic displays to create 3D images. You need to be able to render objects and focus your eyes at different distances, which is different from a traditional screen or display where you only need to focus it at one distance where you're holding your phone or your monitor is. You need a display that can cover a much wider angle of your field of view than traditional displays. And having retina level resolution across that whole field of view requires way more pixels than anything on a traditional display. You need screens that can approximate the brightness and dynamic range of the physical world, which requires almost 10 times more brightness than even what we get on HD TVs today. You need realistic motion tracking, so that has low latency, so that way when you turn your head, it feels like it's positionally correct in the immersive world that you're in. And then to power all of those pixels on the display, you need to build a new graphics pipeline that can get the best performance out of the CPUs and GPUs that we can fit in a headset, without running them so hot that they drain your battery quickly or generate so much physical heat that they get too hot on your face. And of course, you need to fit all that into a device that's comfortable to wear. So if any of these pieces aren't implemented well, it breaks that feeling of immersion, and you really feel that way more than you would on a typical 2D screen today. So we've solved some of these challenges already, and for others, there's still a lot of work to do. Building these devices, it's an integrated effort that includes not just displays, but also state-of-the-art work on software and silicon, sensors, and other hardware that need to work together seamlessly. Today, we're just going to focus on the display system, though. This is the last link in the chain. It's the components that take the final rendered graphical output and convert it to the photons that your eye sees. And it's obviously an important step, and figuring out what we need to do to get it as good as possible was the inspiration for what we internally call the visual Turing test. So now, to talk a little bit more about the visual Turing test, I'd like to bring on Michael Abrash to explain more what that is. Michael?
Hi, Mark. So Alan Turing conceived the Turing test in 1950 to evaluate whether a computer could pass as a human. The visual Turing test, which is a phrase that we've adopted along with a number of other academic researchers, is a way to evaluate whether what's displayed in VR can be distinguished from the real world. And it's a completely subjective test because what's important here is the human perception of what they're seeing, the human experience, rather than technical measurements. And it's a test that no VR technology can pass today. While VR already does, as you said, create a strong sense of presence, of being in virtual places in a genuinely convincing way, it's not yet at the level where anyone would wonder whether what they're looking at is real or virtual.
All right, so today we're going to go through some of the display technology stack and talk about some of the challenges that we're trying to solve. Because as you say, what makes this such an interesting problem is that the core technology to pass the visual Turing test doesn't exist yet in any consumer headset or product. I think a lot of people are going to say, hey, hang on, a decent computer monitor or phone or TV has a pretty good display. So, what makes AR and VR so different? But again, as we've learned, building 3D VR displays that you can wear is a lot more complicated for a number of the reasons that I mentioned before, and that we're going to go into a lot more detail today. So let's talk about why that is.
Yeah, that's right, Mark. I mean, there are a lot of different aspects. The obvious current limitation is resolution, but the challenges are far, far deeper than that. So VR introduces a slew of new issues that simply don't exist with 2D displays, with names like vergence accommodation conflict, chromatic aberration, ocular parallax, pupil swim. And before we even get to those, there's the challenge that AR/VR displays have to fit into compact, lightweight headsets and run for long periods off batteries in those headsets. So right off the bat, this is just really difficult. Now, one of the unique challenges of VR is that the lenses used in current VR displays often distort the virtual image. And that reduces realism unless the distortion is fully corrected in software. And doing that is very complex because the distortion varies as the eye moves around to look in different directions. And while it's not actually part of realism, headsets can be hard to use for extended periods of time because of that distortion, and also because of the headset's weight, both of which can cause some temporary discomfort and fatigue. Another key challenge is around the ability to focus at any distance.
Yeah, so the basic thing here is your eyes try to focus, and you can't because the display is projecting as if it's at a fixed distance. As we've been working through this, we focused our research on a couple of key areas that we think have the best possibility for making a jump forward here. And the first is the most obvious, like you said, resolution. And this is what most people think of when you talk about display quality. And even here, VR presents some unique challenges compared to traditional displays. So maybe you can get into that.
Well, the problem with resolution is that VR headsets have much wider fields of view than even the widest monitor. So whatever pixels are available are just spread across a much larger area than for a 2D display. And what that means is that in any given area, you have fewer pixels, so you just get lower resolution for a given number of pixels.
So we estimate that getting to 20/20 vision across the full human field of view would take more than 8K resolution. And now because of the way that the human visual system works, you don't actually need all of those pixels because our eyes don't actually perceive things in high resolution across our entire field of view. Parts that you're focusing on you see in very high resolution, but your periphery is in a much lower resolution. But it's still way beyond what any display panel currently available can put out there today.
Yeah, and not only are a lot more pixels required, but the quality of those pixels needs to increase. So today's VR headsets have substantially lower color range, brightness, and contrast than laptops, TVs, or mobile phones. So VR can't really get to that level of fine detail and accurate representation that we've become accustomed to with our 2D displays.
So the challenge that we set ourselves here is to find out what it would take to get to a retinal resolution headset. And that means getting up towards about 60 pixels per degree in the display, which is about a few times more than where we are today. And our display systems research team had to get pretty creative to get there. So here is a look at a prototype called Butterscotch, which has enough resolution that you can read the 20/20 vision line on an eye chart in VR, the kind that you'd go when you were going to get an eye test to see if you needed glasses. And these prototypes, they're kind of custom and bespoke models that we built in our lab. So they're not products that are ready to ship. But I mean, when I go and try this out, it's a pretty amazing experience, and you can really see the image incredibly sharp.
Yeah, so this is the latest of our retinal resolution prototypes, and it gets us to near retinal resolution in VR, 55 pixels per degree, and that's 2.5 times the resolution of Quest 2. So there are currently no display panels that support anything close to retinal resolution for the full field of view of VR headsets today. So what the Butterscotch team did was they shrank the field of view to about half that of a Quest 2 and developed a new hybrid lens that would fully resolve the higher resolution. And as you say, that prototype is nowhere near shippable. I mean, it's heavy, it's bulky, but it does a great job of showing how much of a difference higher resolution makes for the VR experience. And I have to say, the first time I put it on, it was almost felt like, well, it's hard to go back now because it was just so sharp.
Yeah, it was a pretty impressive demo, but as you say, we try not to ship things with exposed circuit boards. So as soon as we started testing this, it became pretty clear that true realism needs that certain level of resolution. And what we expect is that the display panel technology is going to keep improving generation after generation, and in the next few years, we're probably going to get there, somewhere like that. But the truth is that even if we had a full retinal resolution display available right now, the rest of the graphics stack wouldn't really be able to deliver realistic visuals. And that goes to the second major challenge that we need to solve around depth of focus. So let's get into that now.
Yeah, we realized that this was an issue around 2015. So that was back when Oculus shipped the Rift and then shortly thereafter shipped the touch controllers. And that first brought a sense of hand presence to VR. And what that made us realize was that once hands are really there, which they are now with hands in Quest, that you would really want to be able to focus on them to use them as effectively as possible. Now, that may seem obvious and truly unexceptional at this point because that's exactly how things work in the real world, but it's not how things work in VR. This is really one of those cases where the rules completely change in VR. And the reason is that in the real world, the lenses of our eyes change shape constantly to focus on the distance of whatever we're looking at, and that properly images the light that comes from that distance. But that's not the case today in VR.
So the problem that we ran into here is that, unlike our actual eyes, current VR optics use solid lenses which don't move, right? And they don't flex. So that means that the focus point is fixed. And we usually set that to somewhere around 5 or 6 feet in front of you, so that way you can see things that are further out, but the issue is that virtual objects much closer send conflicting signals to our visual system, and there isn't really an easy way around that with a single solid state lens. So, our eyes are pretty remarkable, and they pick up all kinds of subtle cues when it comes to depth and location. And when the distance between you and an object doesn't match the focusing distance, it can throw you off and be a bit uncomfortable. And your eyes try to focus, and they can't quite get it right, which can be tiring and can lead to a little bit of blurring. So retinal resolution alone on the display isn't enough. you also need retinal resolution displays that can support a depth of focus that can hit 60 pixels per degree at all distances, ranging from near, so you can read a book that's pretty close to your face, to something that's pretty far away, so you can see the details of the leaves on a tree, for example. And this is another example of how building for 3D headsets is so different from existing 2D displays, because when you have a computer monitor, it's at a fixed distance and you're only focusing there. You don't need to be able to look at objects that are rendering closer or further. So to address this, we came up with a way to change the focal depth to match where you're looking by moving the lenses dynamically, kind of like how autofocus would work on a camera. And this is known in the industry as varifocal technology. So in 2017, the team built a prototype version of a Rift that had mechanical varifocal displays that could deliver a proper depth of focus. And it used eye tracking to tell where you were looking, and real-time distortion correction to compensate for the magnification effects of moving the lenses and any rendered blur, so that way only the things that you were trying to look at were in focus, just like if you were trying to look at something close by in the physical world.
Right. And then once they had that prototype, they ran a study to see if people actually preferred this varifocal technology. And on one day, they would enable varifocal fully on the prototype, and on the other, they would just operate it in fixed focus mode. And what they found was that the majority of participants preferred varifocal over fixed focus VR. They were more comfortable in every respect. They experienced less fatigue and blurry vision. They were able to identify small objects better. They had an easier time reading text, and they reacted to their visual environment more quickly.
So here's the prototype, and once we had this feedback, the team put all their energy into getting the size and weight down and expanding the field of view. And the series of prototypes that they built, which we call Half Dome, ended up using fully electronic varifocal based on liquid crystal lenses, which are much smaller. And even with all this progress, there's still a lot more work to do to get the performance of the varifocal hardware fully optimized, while also making sure that the eye tracking is reliable enough to make this work. So this sort of feature needs to work for everyone all the time. So it's a very high bar. But after resolution and focus, there are other things that we need to work on too. Another major challenge is the distortion that's produced by VR optics, like the kind that are in here. So we've built a number of ways to compensate for this in the software in Quest. It's a pretty good approximation for now, but it isn't exactly right. A lot of the time, because the distortion of a virtual image changes as your eye moves around to look in different directions. And our algorithms are pretty static, so that means that they don't work perfectly when you look around a scene. And this matters for overall image quality because it makes everything move just a slight bit as the eye moves, which can make VR seem less realistic overall. So the correction that we do needs to be dynamic as the eye moves around, and it needs to work across all the different depths of focus that varifocal technology supports, and it also needs to be fast enough that the adjustments are imperceptible, which for visual perception is pretty fast. All right, so this is a quite a hard problem to solve, but it has the potential to produce images that are always stable, which static software correction systems can't do.
Right. The problem with studying distortion, though, is that it takes a really long time. Fabricating the lenses that you need to study the problem can take weeks or months, and once you have them, you still have a long process of building a functional display system with them. So to address that, what the team did was they built a distortion simulator that uses virtual objects and eye tracking to replicate the distortion you would see for a headset for a given optics design and display it using 3D TV technology. So this allows the team to study different optical designs and distortion correction algorithms without needing to build an actual headset. With this unique rapid prototyping capability, the team has been able to explore dynamic distortion correction in literally minutes rather than months.
Yeah, so that's a big improvement. Eye tracking is also an underappreciated technology for virtual and augmented reality, and it's how the system knows what to focus on, how to correct optical distortions, and which parts of the image it should devote more resources to rendering in full detail. And that last part really matters because the thermal and power envelopes for a smaller headset are so constrained for wearable devices that you're always trying to squeeze every last bit of performance out of the system. And if you can just render the parts that you're focused on in the most detail while having the periphery be in lower resolution like the physical human visual system, then that's potentially a very important optimization. So that brings us to the last major frontier in display technology. And this is a big one too. Because while resolution, varifocal, and distortion all make a meaningful contribution to realism, arguably the most important dimension of all is high dynamic range, or HDR. Basically, it's the overall brightness and contrast of a display. Because our experience is that when lights are bright, you see colors pop and shadows are dark, and then that's when the scenes really start to feel alive. But the issue today is that the vividness of screens that we have now compared to what your eye sees in the physical world is off by an order of magnitude or more. So let's get into this in a bit more detail.
The key metric for HDR is nits, or how bright the display is. And research has shown that the preferred number for peak brightness on a TV is 10,000 nits. And the TV industry has made progress in introducing HDR displays that move in that direction, going from a few hundred nits to a peak of a few thousand today. But in VR, the maximum nit level right now is about 100 on Quest 2. And getting beyond that with a form factor that's wearable is a big challenge.
Yeah, so we're going to need to get to significantly higher brightness levels than what we refer to as HDR on traditional screens today. And then, of course, the challenge is we need to do that in something that is battery-powered and comfortable to wear. So, to try to figure out the best path forward, our display systems research team built this prototype, or I guess this is a part of the prototype, that basically puts an incredibly bright lamp behind the LCD panels. And this one's pretty heavy, so we have these handles so you can hold it like that. But as far as we know, this is the first HDR VR system, and internally we call it Starburst. It's, to be clear, wildly impractical in this first generation for anything that you'd actually ship in a product, but we're using it to test and for further studies so we can get a sense of what the experience feels like. And the goal of all this work is to identify which technical paths are going to allow us to meaningfully improve in ways that start to approach the visual realism that we need. And if we can make enough progress on retinal resolution, and if we can build proper systems for focal depth, and if we can reduce optical distortion and dramatically increase vividness, then we have a real shot overall at creating displays that can do justice to all the beauty and complexity of physical environments. But it's going to take a bunch of iterations on each of these technologies to get there, and then we have to integrate them all together. So we're also looking at some further out solutions that could enable us to take big leaps forward. And at the same time, we're working on how to package all these different technologies into smaller, lighter, and ultimately affordable headsets. So today, we have two more things to show you that are going in exactly that direction, trying to take everything that we've learned from our research and trying to bring them together into a compact form factor that could plausibly get us to visual realism. These are all still prototypes, but they represent pretty meaningful steps towards technology that could one day deliver breakthrough products. So the first one up is an experimental device that brings together some of the latest optics research into a fully functional headset that is unlike anything that exists today. This one we call HoloCake 2. It is the thinnest and lightest VR headset that we've ever built, and it can run any existing PC VR title. In most VR headsets, the lenses are pretty thick, and they have to be positioned a few inches from the display so they can properly focus and direct light directly into your eyes. And this is what gives headsets that look where they're pretty front heavy. But HoloCake 2 introduces two new technologies to get around this. The first one is that instead of sending light through a lens, we send it through a holograph of a lens. And holographs they're basically recordings of what happens when light hits something. So, just like a holograph is much flatter than the thing itself, holographic optics are much flatter than the lenses that they model. but they affect incoming light in pretty much the same way. So it's a pretty neat hack. The second new technology is it uses polarized reflection to reduce the effective distance between the display and the eye. So instead of going from the panel through a lens and then into the eye, light is polarized, so it can be bounced back and forth between reflective surfaces multiple times. And that means that it can travel the same total distance, but in a much more compact package. So the result is this thinner and lighter prototype than any other configuration. But as with anything, when you're building these integrated systems, there are trade-offs and there's a catch. So Michael, you want to take us through that?
Yeah, that catch involves getting the right light source. So HoloCake requires specialized lasers, and that's pretty different from the LEDs that are used in today's VR headsets. And lasers aren't that exotic these days, but they're really not found in a lot of consumer products at the performance, size, and price that you need for consumer VR headsets. So we'll need to do a lot of engineering to achieve a consumer viable laser that meets our specs, that's safe, low cost, and efficient, and that can fit in a slim VR headset. As of today, the jury is still out on finding a suitable laser source, but if that proves tractable, there will be a clear path to sunglasses-like VR displays.
I'm quite optimistic about the direction that all this is heading. Now, a big part of your job, of course, is trying to imagine, all the future technology that we're going to need to solve, and the state of what these technologies will need to be in, 5 to 10 years from now for the multiple generations out of devices that we're building. And I think you have one other design that you wanted to show today. Is that right?
Yep, we have one more design. So ultimately, the goal, obviously, is to bring together all of the technologies we've talked about, integrating all the visual elements needed to pass the Turing test into a lightweight, compact, power-efficient form factor. And we're designing the Mirror Lake prototype right now to take a big step in that direction. So Mirror Lake is a concept design with a ski goggles-like form factor that takes the HoloCake 2 architecture and then adds in nearly all of the advanced visual technologies that we've been incubating over the past 7 years, including varifocal and eye tracking. It shows what a complete next-gen display system could look like. So the key here is that thanks to holography, everything is thin and flat. The varifocal technology is flat, and so are all the holographic films used for HoloCake, as well as prescription correction and eye tracking. And so it's easy to keep adding thin, flat technologies. This means that the end product can pack more functionality into a smaller package than anything that exists today. Now, the Mirror Lake concept is promising, but right now it's only a concept with no fully functional headset yet built to conclusively prove out the architecture. But if it does pan out, it will be a game changer for the VR visual experience.
And I hope that this has given all of you watching today a sense of some of the fundamental challenges in getting to visual realism. Now, one of the reasons why this is such an exciting space to work on is that this is genuinely new technology. Right? We're not just refining the types of screens that we've had on phones or TVs or computer monitors for decades and that already exist. And we have to explore new ground in how physical systems can work together and how our visual system perceives the world. So, I think that augmented, mixed, and virtual reality, that these are going to be fundamentally important technologies, especially for delivering this sense of presence and improving our social interactions. And we're starting to see them come to life, which is really neat. And if we can continue making progress on the kinds of advances that we've talked about here, then I think that that's going to lead to a future where computing is built more around people and how we want to interact with each other and how we want to experience the world. And I think that that's going to be a lot better than anything that we have today. Okay, so that's just about it from me. But if you want to go deeper on all of this, then I recommend sticking around for the rest of this session. Up next, we have Doug Landman from the Display Systems Research Team, which is responsible for all of the prototypes that I showed you today. And I also want to thank Michael for being with us today as well. All right, over to you, Doug.